Well, you know, from a operating standpoint, practitioner standpoint, Craig and Ryan, what they've done at the Stone Edge winery and farms is amazing. They've literally taken a facility and experimented on it on such a level that it's probably one of the most sophisticated microgrids for not only what they do there, but for learning and for new technologies with their fuel cells. And I'll just stop right there because these are the experts. I was honored to have been there twice, to have participated in a 2-day seminar, and I got to see 2 tours, and I learned so much more on what they're doing there. This is cutting edge. There are, and you can go through the different national labs and groups that use Stone Edge and what Craig does there as a learning facility worldwide. So Craig is the CEO of Wooster Engineering. He's also a general contractor. And you know, this is one of the leading authorities in microgrids and on-site storage. So, and this is his assistant here, Ryan, and I'll let them give him a nice round of applause for coming out here today.
Thanks, Carlos. You rock. I envy you so much. All those floors, though, man, it's like, oh my God, my head would boggle. So, my name is Craig Wooster. I'm the general contractor and project manager on the Stone Edge Farm Microgrid project. What we're going to do today is we're going to do a brief overview of the project and talk about how it got started and where it's gone. And then I want to focus a little bit on what we think is important for you guys. How did we get started? Here are the 2 people. Unlike all of you, you're all going to envy us by the time we leave here today. We have no government money. We have one man who writes our checks, which makes us very agile, capable of doing whatever we need to do. One of the founding principles of this project, we'll be talking about it, is what we call the prime directive. But it actually says in my contract that I will not take costs as the first determining factor in an acquisition. Talk about freeing your mind. That changes everything right there. It also says, you will not fear failure. Failure is the crucible of success. You must fail to learn. You will do some things twice and some things 3 times. Ryan and I will tell you we've done more than 2 things 3 times. So, while people like to call us experts, the reality is we are learning at a snail's pace. This project's been going now for 4 3/4 years. It's started with a vision. My contract says, build a microgrid. That is all the direction we got. This is an open source project. Everything that we have learned is available to anyone. So that has brought people to our table that you wouldn't expect. Bornsford Labs, EDF, that's Electra de France, E.ON, the largest German utility company. Everybody but our own utility companies is actually involved in this. This is what we call the prime directive. I like to state it a little differently. I am allowed to build any system, procure any device, as long as it reduces the carbon footprint of Stone Edge Farm. The original goal was 50%. We accomplished that in the first year, and everyone of you know how. We just solarized. It was simple. But then we began to look at storage. And we were building a microgrid, which by definition requires us to be able to do some things. Here's the primary directive. The term microgrid, unfortunately, is about the worst word on the planet. Most people conceive of a microgrid as a group of wires and switches and controls. I'm going to tell you that's not really what it is. It's a state of mind. Microgrids, distributed energy resources, and distributed energy generation is more of a philosophy. It starts with something as simple as a single solar panel, and it grows to the enormity of what we've been doing at Stone Edge Farm. We're not done. That's the point that I want to make sure you understand. Our adventures have taken us, here's the Department of Energy's definition of what a microgrid is. So this was kind of our guiding light when we started. and heading in some direction with it. We then began to get to the point where we said, well, how does this fit us? Stonehenge Farm is 16 acres, 16 buildings, 7 incoming utility service entries, that's 7 meters, all inside of a rock wall. Over the course of the last 4.5 years, we connected all 7 of those service meters together. We can actually island ourselves from the utility and operate completely autonomously. Behind that wall, we have put 3.5 times more generating and storage capacity than we will ever use. Because at the time, we were working towards the theory of a microgrid, and our big goal was to be able to export electrons. Right about the time we submitted to Pacific Gas and Electric for a connection agreement, we also started to look at hydrogen as our bulk storage medium, gaseous hydrogen. We got a very polite letter back from our utility company telling us that there was no way under the current Rule 21 in California for a microgrid to connect to the grid. The only course of action for us was to go through the CalISO process, which we have entered. Unfortunately, right as we were doing this, we began exploring hydrogen and producing our own hydrogen from the sun. So today, Ryan and I drove here in a hydrogen-powered car that we drove halfway here on hydrogen made from the sun. Unfortunately, because neither of us were smart enough to fill the car up yesterday, we couldn't get it back. We had to stop and get fuel. But my car has not been to a commercial fueling station for the last 4.5 months. And I drive it every day. So you know how many times you go to a gas station. We are filling 3 hydrogen cars right now. 2 of them driven by our line staff, 1 driven by myself. And we are running those cars completely on hydrogen we produce from our solar. And we are capable of producing hydrogen 24 hours a day. We don't because the hydrogen production, our current system is very noisy, which upsets our neighbors. So we're allowed to operate between 7 and 5. Let's see, I'm coming up right there. So what I wanted to do is give you guys a quick introduction to who we are, what we're doing. And I'm going to pass this to Ryan. Ryan Stoltenberg joined our project, I think, 4 months in. He had just graduated from UC Chico with a degree in environmental sciences. He spent the first 9 months of his employment in a ditch with a shovel and a pick. The problem that we had to do with the 16 acres, there was so much stuff in the ground that most of our trenches had to be done by hand. So he started out as the shovel and pick expert. Then he got to operate an excavator. Then he decided, I'm going to go back and get a master's degree because there's got to be another thing in this world to do. So he has subsequently, just recently in June, completed his master's degree in environmental sciences, and his thesis was written on our hydrogen production facility. Ryan, take it away.
Thank you. All right. So I'm going to go ahead and give,
I asked, the shovel and pick training, did you get that in college or after?
right afterwards, it was on-the-job training. Also, jackhammer was used predominantly because the soil in Sonoma is very, very rocky. So you got to break through the couple foot layer of rock first.
So was there utilities already?
Yeah. So like Craig said, that there were 7 incoming utility meters. Some of them were 480 because it was industrial for, there's a shop on site that they use drill presses and 480 volt equipment. And then a few of them were 208 3-phase and 240 split phase. So we had to connect all of those together. So our main trunk line that we've connected all those meters together is now 40 volt 3-phase. And it's the largest trench that we had to dig on site between all of our meters. So that was the main haul of upgrading our infrastructure to be able to do the production that we have on site now.
Are you using one string inverter for these different arrays, or are you using micro?
So we use micro inverters from Enphase right up here. For all of our arrays, we actually have 7 arrays total. All of them are distributed throughout the property. So I'm going to get to that very soon.
And Brian, feel free to take that microphone out if you want. There you go.
Thank you. Okay,
So this is the slide for generators. I'm going to go through the technical details of basically everything that we have installed on site here, from generation to storage, and then I'll talk about hydrogen as well. So generation, our primary generation is from solar. We have about 380 kilowatts installed right now throughout the 7 arrays, like I was saying. So this is one of our first installed arrays. This is up on our northwest side on our ag building. This is another array that's installed on our Zen Spa. I know that we gave a tour to the guys that came out to the Institute training of the Zen Spa facility. So all of those are distributed throughout the property, like I said, and those are all feeding into the microgrid trunk line. So we can then distribute the energy that we've created from solar and use it throughout the property. We're very solar rich on the north side of the property and very load heavy on the south side of the property. So we're distributing all of that generation down to where we actually need the energy and then charging and discharging batteries throughout. So we also have a Capstone C65 micro turbine. So that's running on natural gas. That's our only generator that's non-renewable, the only energy storage or usage that's non-renewable. So when we installed that, they basically, PG&E threw out our net metering agreement immediately because they couldn't track if the energy that we were exporting was from the solar or it was from the turbine. So that system is running about 29% efficient by itself. So we've actually installed a tri-generation system, kind of like the one that Carlos showed in the pictures, not quite to the scale that they're using in Shanghai. But we've got a 10-ton Yazaki absorption chiller connected to our, we're exploiting the waste heat coming off of our turbine and collecting that in the form of hot water, storing it in tanks and running it through the chiller to create cold water as well, and distributing that through 2 spas and 6 buildings, I think. So that increases the efficiency of when we're actually needing to run on the Capstone when we're in the middle of the night. Maybe we need to charge some batteries. Yes?
The term tri-gen.
Tri-gen.
I've dealt with cogen in the past on the absorption chiller side. I've never come across the term tri-gen. How does it differ from cogen?
So
Or
They're
semantics.
the semantics. So tri-gen is typically considered that you have a heating load, the electrical load, a heating load, and then a cooling load. And that's really the tri-gen portion of it. But cogen is what all of us, anybody over 30, that's where we've seen it for most of our lives.
Do you do any cooling of the inlet air for the turbine?
We haven't yet, and I don't want to take the fire away from Ryan. One of the things I want to point out is we have 10 different kinds of inverters. We have no inertia in our system, no reciprocating mass. Even though the Capstone generator is a natural gas fired unit, it is in fact,
Sorry about that. It's in fact a DC generator. It's a jet engine in a box. A DC generator that has batteries on the bottom. It charges the batteries, and batteries send the energy out through an inverter. So that's kind of the holy grail of the future of microgrids, is to have no inertia from non-renewable sources, i.e. a diesel, propane-fired
What
generator.
about supplementing with methane generated from biomass that you guys produce?
Well, we did look very closely at biomass. We are actually taking another look at it on a second property that we're doing. This is the first of a number of microgrids that we are building. One of the problems there, the Prime Directive limits us to, if we cannot figure out a way to deal with the CO2 as a byproduct of the biomass usage, then we can't use it. In conjunction with UC Davis, we are actually working on a system. We've built an alpha model of it, where we're using algae to capture that CO2 from the whatever process. It can be the CO2 left in a point source like a turbine, or from a biomass generation, and then whatever you used it with, an internal combustion reciprocating engine, or a turbine, or now to talk about fuel cells. Even in the fuel cell system, what we're using the methane for is to crack the water molecule and get the hydrogen. Well, now we got to do something with any of the carbon left over, and oxygen's not a problem. So, sorry.
You're fine. Yeah, feel free to ask questions because I'm being brief. Yes.
Just kind of adding on to that, do you have any exploration with mycella? Using fungi?
Fungi.
We have, again, that's a UC Davis.
That's a UC Davis thing. We're collaborating with UC Davis, UC Irvine, who is probably the premier leader in the microgrid space right now. There's an ICE-PAG conference at UC Irvine every year. Any of you that are interested in microgrids, I strongly recommend that you put your application in for that with your schools and get to go to there. I will tell you they are the leaders in fuel cells and microgrid development. Dr. Samuelson and Dr. Brower. We're also involved with UC San Diego, MIT, Northwestern University, University of Chicago. I can go on and on.
Thank you. Good job.
Have you
Tried it.
We did a absorption, small absorption chiller using solar thermal as the heat source. Have you done any of that?
Poor Ryan. So, as you well know, you've got to get the temperatures up. So, I have in the past. One of the things that I want to really look at, and this is as we're going to switch our Capstone over to operate it on hydrogen. We were originally doing this in conjunction with UC Irvine, who has already done that. They wrote a white paper on it that's available, open source to anyone who's interested. Right at this moment, this very moment, Capstone and Argonne Labs are working on a joint project funded by the Department of Energy to retrofit a Capstone generator to run on pure hydrogen gas. So one of the problems, like with running on hydrogen gas or some of the other sources we have, is we can't get those temperatures up. But if we can take the lower temperatures and run it through solar thermal, particularly in a series parallel system of panels, everybody know what I'm saying when I'm saying a series parallel series of panels? We could then control the temperatures within the specifications of the absorption chiller. Now, on our project, we have a combined heat cooling element, but we are not allowed to use a cooling tower. Get your heads around that. What do? Just so happens we have 6 geothermal wells that were dug for a geothermal cooling system. We're taking the water and running it back through the geo wells to lose the heat before we can re-enter the process. So part of what we do is try to think outside the box. And that's where, we also have an intern program. All of you should be aware of that. Over the course of the 4.5 years, we've had 55 interns. They range from high school students to postdocs. They're from all over the country and all over the world. India. Right, we currently have 2 master's degrees students from India who are working on the project. If we want to accomplish things, we have to start thinking about outside of the United States, especially with innovation. And that's why Carlos and his work outside is so important. Did I answer the question thoroughly? I'll just stay standing up.
Okay, so I'm going to move into energy storage. So we, like Craig said, we have 9 inverter systems on site. So integration is a big thing for us, making sure that all these things can play together. Because as you guys know, integration is really an issue when it comes to having things that are speaking different languages. So you have your batteries that are giving an output of some language and you need your control system to be able to send a request in another. So we're using lots of different systems and trying to get them all to be able to work cohesively. So we have our largest battery pack is a Tesla power pack. So that's 5 50 kilowatt refrigerator sized batteries. Those run through a DC combiner and to a 250 kW Dynapower inverter. Yes?
What's one of those cost?
Good question.
$500,000?
$500,000. So that is our largest battery system, and that is, we just actually overrode that hardware software, to be able to run as a master inverter. Tesla, we talked to them and we're trying to work with them to be able to set that into master mode. We could, it's the grid tie battery system, so it only wants to be running as a slave, so it doesn't want to set its own frequency, it wants to just load follow. So we had to bypass, our MIT controls expert, Jorge, was the one who did this project. But we are now running in master mode with our Tesla, and that can basically hold up our entire system. We sit at about 100 kW baseload. That's kind of the peak baseload that we see on site ever. So having that battery fully charged keeps us pretty well off, and keeps everything live so that we can then make decisions in our control software to bring other systems up off of the Tesla. So our second largest would be our Aqueon batteries. So those are palletized aqueous hybrid ion batteries. So they're basically saltwater batteries. They're huge. They're about 4,500 pounds each. So, and each one of them is 48 volts. So they're deep cycle batteries. So totally different application than the Tesla, which is lithium ion cobalt, which is really strong punch, hits you hard, just like that's why it's so perfect for cars. You wouldn't want to put an Aqueon battery in your car, ever. So we have a containerized, a container of pallets of these Aqueon batteries. There's 14 of them, and those are connected to an ideal power inverter, which is a 30 kW. Each one of those is connected into 7 battery strings, and those the ideal inverter has a dual DC bus, so 2 DC inputs, 1 AC output, so you're not dealing with high voltage DC, which is dangerous. So that's running in with about 250 volt strings, and that's a 480 volt output. So we were running the entire system on just that inverter for testing for about the first year and a half before we made the Tesla be able to work in not just slave mode. So then we have our ESS, Energy Storage Systems. That's a Portland-based company, and they have an all iron flow battery. So again, that's a large footprint battery. It's a 20-foot container, and that's only a 10 kW battery. So again, use cases. We're building a toolkit of being able to understand all of these different battery systems and what their niche basically is, and trying to run them all in one system. So this guy's really good for time of use for solar. If you have a small solar array, this is a deep cycle battery, and that's running off of and that's a 480 volt 3-phase as well output with the Outback inverters. And then we have a few different deployments of some simplified lithium ferrophosphate batteries. So it says 34 kW up there, but we have 2 arrays that I think are about 10 kW, and then we have about 4 kW. Those ones aren't currently connected because we've had some issues with Schneider. That's one of the only inverters that we've run into problems with. It doesn't really like to play with our control system, so we're working out the kinks on that right now. Then we also have a Sony lithium iron phosphate battery, which is basically a large uninterruptible power supply. So that's a 10 kilowatt, and that's connected directly to our servers. So that is a battery backup directly for one single use. So that's not in our control system. That's continually being trickle charged by solar, and it's directly connected to the panel that our servers are on. So communications is another big critical junction in a microgrid, because if you lose communication, you lose the ability to make decisions, and you have to be able to send set points, turn things on and off, even when the macrogrid fails. So that's what we call our critical grid. So we have our microgrid trunk line, which is running around 480 volt 3-phase, and then we have our critical grid lines that are just spurs off of that are all 120 single phase for critical systems. And then that brings us to hydrogen, which is like Craig said, our main means of energy storage. So we're not charging and discharging these batteries every single day. That obviously degrades the systems if you do that too often. So we're running our electrolyzer when we have overproduction, and trying to stay net zero because we don't want to flood the grid with too much energy when we can be creating fuel and utilizing it. So our hydrogen generator, let's see if I get a slide for that. I'll go back to that. So our hydrogen generator is in our little power plant up at the northwest corner of the property. So that is a electrolyzer, which is basically a generator that's using electricity and water to crack them into the constituents of hydrogen, H2, and oxygen, which is a very energy-intensive process. So a lot of the hydrogen that's produced now that's used at the commercial stations is gas, steam reforming, gas steam reforming. So that's not technically renewable because they're doing that off of natural gas. But we're running off of pure solar, like Craig was saying. So then we also have stationary fuel cells so that we can directly bring that electricity right back off of the solar when we need it. We've got about 26 kW of, those are rely-on fuel cells. And those are also paired with solar. So this is an overview of our resources based on spatial. So the Capstone's in the bottom corner, and this main connection at the top here is our common coupling to the grid. So when we go into island mode, we shut off all of these PG&E inlets on the right and leave that one open to last. Any questions?
I got one comment to make, and then I'll give it away to Charles. With the use of electrolysis for generating hydrogen, how effective is that being for you? It's a process I've long thought as a way for helping us move forward and away from fossil fuels to use overabundance of renewables. At times we can't use them and generate hydrogen to run through a hydrogen or through a fuel cell. How effective has it been for you at this point?
So let's kind of walk through your question. I put a solar panel on the roof. What is the marginal cost of a photon that strikes that panel? What's the cost of it? Anybody? 0. Okay? What's the marginal cost of a kilogram of hydrogen made from the electricity generated by that solar panel? Close to 0. It's 2.3 gallons of water. Because that's how much every kilogram of hydrogen takes, 2.3 gallons of water. Here's the rub. That water doesn't even have to be potable. What's the marginal cost of black water? It's negative. You can actually get paid to take that black water. And what happens if I take black water, I clean it enough to go through the hydrogen electrolyzer, I break it with photons made from the sun, and then I run it through a fuel cell. What do I get? I get a pure drop of water. 100% pure. Doesn't taste very good, but it's pure water. And I've actually taken water from the exhaust of the Mariah and drank it. It's flat, that's the problem, no minerals. So your question really is a question that is now kind of getting out of date. Because all we're really talking about is the initial CapEx to build the project and the O&M to maintain it. And this is, the costs get a little more expensive with wind. But with solar, as everyone in this room now knows, we've got enough track record with solar. We know panels last more than 25 years. I have panels in the field older than 25 years. So we have to start to change our thinking. Yes, the process itself is only 66% efficient. Right? Think about it. 2 hydrogen, 1 oxygen. We got to break those bonds. We're never going to get above 66% efficient. Right? There's no way. Because you've got that energy to get that oxygen out of it. So right now, the question is, are we going to move into the future and look at energy curtailment in California? How many here are from California, or maybe how many here are outside California? Okay. So, for those of you who don't know about California, in April of this year, we had an 8 megawatt curtailment of solar. We're projecting multi-gigawatts of curtailment of solar and wind this coming year. I kind of thought intuitively that curtailment would occur only in the key solar months of the year. The reality is there's curtailment every month, and if you log in to the Cal ISO website and ask for the curtailment maps, it'll chart for you what the curtailment is on a daily, weekly, monthly, and yearly basis. So what does that mean? In California, our cost of electricity during curtailment actually goes negative. The state of California is paying to get rid of that excess energy. Yes, we in California are crazy. There's absolutely no question about it. So, the California Energy Commission just issued a grant funding opportunity to build a hydrogen production facility. They're giving $3.9 million to build a hydrogen production facility that can produce 1,000 kilograms a day. That's fundamentally what that project's about. As we drove over here, I was on a conference call with a company called Photon Onsite. They're the manufacturer of a hydrogen electrolyzer, and asking them if they would team with EPRI, Electric Power Research Institute, EDF, Electric de France, Stone Edge Farm, to go after this grant to produce that hydrogen partially from curtailment. So just think about the business model of this. In the state of California, if you produce a kilogram of hydrogen, the state will pay you $2.17 in a hydrogen low carbon fuel credit. That's all I have. I got $2.17 to start. I haven't done anything else. Now what happens if I make that hydrogen from curtailed electricity and I'm being paid $1.45 a kilowatt to take the electricity? Got any business majors in here? I don't even need a napkin. Okay? We are living in the most dynamic times. This is an energy revolution that's taking place. The shot's already been fired. The shot heard around the world. The shot heard around the world. Here's the interesting part. What we're learning today, China is implementing faster than we can think of the new things. Did I answer your question?
Yeah, you did. You brought up, like you said, some new concepts on how it's old. So there sounds like there's good application potentially, since there's black water involved, for any wastewater treatment facility around the nation. And so that their generating capability to cut municipal costs could be tremendous for something like this.
Yeah, business 101. A water treatment plant is a liability. Anytime I can take a liability and turn it into an asset,
Yep.
I'm done.
Thank you. Charles?
It was briefly touched on, but I was curious. You're talking about microgrids, so obviously you guys can't do you're not doing net metering. So you're making your own power and you're having to sync this power to whatever it is that you're creating for a grid. Well, obviously the grid thinking of it as a very large ocean. You're basically syncing everything to the waves of the ocean in a grid system where I'm net metering. I mean, I can't affect the grid's frequency, but in your case, you really can. I mean, so you touched on the Tesla battery pack becoming your primary. What are you doing right now in order to tie all these little inverters together, all these different systems together, in order to maintain frequency and voltage?
That is a good question. That is a lead-in to our controls. So we have a tiered control system. So we have a tertiary control, which is DC systems. They're on both sides of the meter. They write the software for PG&E, and they also have access to our assets. So they can reach into our servers and allocate voltage, amperage to run around our property or send out to the grid if they want. So that's our tertiary control, so that's completely remote. They're never on site, they reach in via Ethernet. And then we have Emerson, which is our Ovation platform. So that is it's basically power plant software to monitor and control generation, battery charging, anything that we would need to do is all controlled in that system. But our black box, which is what's doing everything that you're saying, is our HALAs. It is a startup company that was started by our MIT controls expert. His name's Jorge. He built this as a asset level controller. It's a smart gateway is what he calls it. So it's accessible by him via Ethernet. He can reach in, he can look at every asset that we have on site, see what it's doing, tell it what to do, turn it on and off, see its state of charge. see its frequency, make sure that there's no issues. He has set points set in there for alarms. He can do optimization. He can decide which things to use and relay that information back to Emerson or DC Systems. And it's basically a catch-all for any asset that you could install in a microgrid. If you have a battery, you have a generator, you have solar, you have Capstone, microturbine, any of that stuff, you can put one of these boxes. It's called a HALA IQ, and it's a control box that is on every one of our assets, and it's basically making decisions between the control system and the asset level. So when the control system reaches out to send a command, it's talking to the HALAs specifically, and they are the ones that make the final decision on what gets done.
So communication is the key then, if you can't communicate, because it's basically virtual, really. I mean, there isn't really you're not, they're virtually trying to stay exactly the same as what it comes down to, and that is your head controller. Correct. Then for, it's not producing power, but it's making sure everything works together.
Right.
Interesting.
And it also goes back to communications. Like I was saying, all these things speak different languages. HALA is communications agnostic. It can speak all the languages that the batteries can throw at it, and it relays that as RS-485 through Ethernet, I think, back to the main control systems. So it just simplifies everything. You can install something that you've never worked with before, and if you put a HALA there, it takes care of it. But your frequency question, that's a question of switching. So when we have automatic transfer switches, which are at our nodes basically, and when we're going from island mode to grid connected mode, that's when the frequency matters. As you guys understand, if you have over or under frequency to your equipment, that's a problem. So that's something that we're still doing testing on, is making that a seamless transition from going from grid tied to island, and that would be directly going from the grid set frequency to the frequency that the Tesla would then be immediately setting. So we have some tricks that we can go to a null position, already have the battery fired up, and then kind of throw the switch, and it'll catch itself up basically. But we're still working on making that able to be automated. So if a tree fell on the line outside, it would go ahead and jump right into island mode by itself without us actually having to catch it or think about it or do anything. So does that answer your question?
Very much, yeah. I was just curious because on big systems, it doesn't matter. I mean, every power plant, somebody making a little wave in the ocean, you know, you have no choice but to match the frequency of the waves that are coming in. In this case, there are no waves. You're making your own, and so yeah, everything affects everything else. They're all very important pieces. So yeah, I was curious, and I perfectly answered my question.
Okay. I am going to skip through controls since we kind of already touched on that, and just give you a brief overview of our hydrogen system. This is built by Millennium Rain. This is actually the electrolyzer. So this is about an 8 by 12 box where the cells are actually in there. So this is generation right here. This then runs underground piping to our storage. We've got 24 kilograms of storage, and that's at 6,000 PSI. So these Mirai cars, they want 10,000 PSI to be give you full range. So we're filling our cars halfway. So that's 35 bar, 350 bar. So we're getting about 150 miles of range on every single fill, and you're getting about 300 miles range when you fill up at the regular station. So that's one thing that we're trying to implement, is a booster compressor, which is, as we've come to find out, very hard to find because hydrogen is this very small molecule. It's very hard to compress. So that's something we're working with Millennium Rain on. So hopefully we'll have a 10,000 PSI compressing booster in the next year or two. And then this is a picture of our fuel cell hives. So there's 3 cabinets. Each one of them has 4 of those 2.2 kilowatt fuel cells. Let's see. So applications, I think I already touched on this a little bit. Chemical industry, so that's gas steam reforming. They've been using it for a long, long time in generating chemicals. So there's already protocols set for it to be transported and all that. So that's already in place. It's just kind of the home fueling, home generation that doesn't have very many lines drawn in sand as far as rules. Anybody? Questions? Okay. So then this goes back to load and peak shaving, which we kind of talked about already, and then scalability. Our system is running at about 30 kW, which is a very small system. They're already scaling up to megawatt scale, which would be for the applications Craig was talking about as far as large wind farms or curtailment. So we're working with Siemens and, like you said, Proton on-site on some larger systems. This is just a quick overview and our electrical drawing, and I'm going to hand it back to Craig.
Great. So a couple things. There was a word that went by there that I want to make sure each one of you focused on. If you haven't, write it down. EasyIO. Okay? How many of you already experienced EasyIO? Okay, and you were laughing, so do you find a problem with it? No. Okay. EasyIO is an open source controller. What we're finding, we actually believe we can operate our microgrid on an EasyIO. Right. And I want to make sure that you know that our top two control systems have already cost over over $250,000 each. And so for $10,000, I can operate our microgrid on an EasyIO system for free, and then I can hand the SIM card to you, and you can go operate yours.
Excuse me. That controller sitting on the desk right there, that's Contemporary Controls, America. And the owner's right back here.
Okay. I'm not familiar with it, so get me informed.
It's the same exact programming scheme.
Cool. Love the
Sedona framework. You guys are hanging out here later today, we're going to be going through it.
Yeah, unfortunately we can't. We have to go to a meeting. But I'm going to leave my cards up here. But I would love to know more about it, and so would our people. We just haven't encountered it. Okay, so during the fire on December 7th, the morning of December 8th, I was woken up at a little bit before 5. My alarm clock would have gone off in a couple of minutes, and one of my project managers said to me, he said, "I can't get to Sonoma, it's on fire." I reached over to my lamp, no electricity. I sat up in bed, could hear the fire trucks zooming on the roads. And I immediately picked up my cell phone and I called my son, who happens to live about 15 steps from Stone Edge Farm. And I called Jorge, who is our tech, and he lives about 200 feet away. And I said, "Put us in microgrid mode now." And the morning of December 8th, at about 5:30 a.m., we went into microgrid mode. For the next 10 days, we operated. Here's what's really funny, and the part that we never expected in all use cases we've written, we were all evacuated. There was no one there. Now, everybody in this room is probably going, "Well, it's a microgrid, dummy, it should sit there and work." Well, we were always figuring that somebody would be around to flip a switch, reset a breaker, do something. For 10 days, we operated totally autonomously with nobody on site. So I apologize for the poor quality of this slide, but if you really want an interesting experience, if you go into Google Earth and you switch to Google Maps and you're looking at Coffee Park, Santa Rosa, this is what Coffee Park looked at like at 7 p.m. on October 7th. This is what it looked like on the evening of October 8th. Burned to the ground. 5,800 homes. Higher view, more than just a Coffee Park area. So we're talking about microgrids. How do microgrids fit into this fire scenario? Well, first of all, they can operate in the fire. They can support the grid. They can provide emergency services. So we're working very closely around schools, hospitals, and fire stations to provide resiliency at those locations first. The market. There's 17.51 billion by 2025. I'm going to tell you that's more like 2022. This wave is going to roll so fast that it's going to make our heads spin. Along with it is going to come hydrogen. Hydrogen is the key to the future. How many people in this room are teaching hydrogen and hydrogen production in your classes?
I used to.
Come back to us. Let your hydrogen free. This is an extremely important point. We're going to need a lot of people, and you are the people who make the people who do the things that have to get done. So I'm going to tell you, right now in California, we need 10,000 people who know what I know. We need 200,000 people who know what my crew knows. And I'm talking specifically about microgrids. Right now, every contractor in California, every architect, I was just at a meeting with the city of Santa Rosa, the county of Sonoma, the state, interested parties around this fire, and we're sitting in a room with architects and contractors, and we're talking along, and I raised my hand and I said, could I just ask a question? How many architects in this room already are under contract on homes in the Sonoma Valley for the fires? Every one of them raised their hand. How many of you are in contract for 3? Every one of them raised their hand. Okay, how many contractors already are in contract? Every contractor raised their hand. And I asked a simple question. How many contracts and how many houses can you actually design in real time? You're already all booked, right? We got to build 5,800 homes, and I'm talking about Sonoma. I'm not talking about Southern California. I'm not talking about Houston, Texas. I'm not talking about Florida or Puerto Rico. This is a huge, this business is one part of it. And why aren't we building those houses as net zero homes? Energy producers, energy exporters. And I'm not talking about net metering. Forget net metering. We're going to go way beyond net metering. Now, our utilities will follow us. You know, when I go speak at conferences and I go all over the country, one of the things I've discovered is the utilities, which are mostly co-ops in the flyover states, are some of the first people who come up to me and go, we want to talk to you about how to do this. Why? Because they have a vested interest in the outcome of the power. Our investor-owned utilities, they don't give a damn. They're not going to give a damn until the whole paradigm shifts. And the paradigm is going to shift because major companies and corporations are going to begin to abandon the grid. Sure, we'll pay you a meter fee. Look at the MGM in Las Vegas. They handed the state, the utility, $65 million to abandon the grid, take the meter away. 2 other companies followed suit immediately, and then the CPUC in Nevada threw in a rule and said you cannot abandon the grid. Why? Because there was going to be a rush out the door. So, last thoughts, we can go through this stuff. So 3 takeaways. I want to know about this controller, but we've got to start talking about simple controls. And getting away from proprietary controls is extremely important. Even though we want to create jobs, we're going to create a lot more jobs by having a lot of people who can do all of these basic things. And as Carlos has pointed out into the buildings, and I didn't hear everything else. Secondly, hydrogen. It's huge. It's the most disruptive technology we've seen. In the words of Mac McGowan, the owner of Stonehenge Farm, this is going to be the largest exchange of capital since the beginning of the Industrial Revolution. Get your heads around that. It's huge. So with that, we thank you. Any questions?
A kilowatt that you have and you start to produce, you use 1 kilowatt of energy to produce some hydrogen, store it, and then you release it in the fuel cell. How much do you get out when
Round trip efficiency is what we're really talking about. About 68%.
you're saying I'm going to get 6.68 kilowatts? So I have 1 kilowatt hour off my solar array. I'm going to go through this process, store it, and I'll get 0.67 kilowatt hours to burn in my car.
It depends on the system. So the point though, when we start talking about efficiency, let's go back to that marginal cost perspective. Once you take away the cost of the photon, right? Now there's a CapEx in there, and we can wrap it in there, and you can play with those numbers. The more you play with them, the more you're going to realize what I'm saying is true. I'm telling people, buy as many solar panels as you can and put them on your roof. Your roof, somebody's roof, your barn, doesn't matter. If you can afford 4, put them up. Why? You go cash positive the day you put them on the roof. Now, every year, or every 6 months, or whatever your budget allows, put another one. Because as you do that, the power becomes free. Now, solar is just one perspective of this, but solar to hydrogen, wind to hydrogen are two of the avenues that we see for energy. And there's right now, Dr. Richard Lester from MIT told us he believes there's over 6,000 battery technologies in development today in the United States. We're only seeing the beginning of this. Any other questions?
Unbelievable work, man. I was going to ask, in regards to hydrogen and creating it, what are you guys seeing as far as the water care piece behind that? You know, what's happening? Do you guys have issues or maintenance things you have to constantly deal with?
Well, if you want to go from black water to the water to an electrolyzer, you're going to spend a little time up front in reverse osmosis perspective. Working with a couple of manufacturers, there is a belief that with the PEM cells and the alkaline cells, that we're going to get to a point that we can eat black water, virtually just strain it. So you start thinking about that water plant. That thing's a money maker, really. It's got a huge capacity. Now, there's a company out of Morgan Hill, California, who has a fermentation process. Results in three byproducts. Steady stream of hydrogen, pure, 3 nines, 99.999. And then it produces two forms of fertilizer. One is solid, one is liquid. We took the liquid, the feedstock in this case was aquatic plants, fed into the front of the system, came out the back. I sent the liquid fertilizer to UC Davis for analysis. They were going, this is beyond any commercial fertilizer in PNN. I mean, it was excellent. There's just a treasure trove of technologies that are being developed right now. If we don't end up put the cap on development and R&D. I think this gentleman had a question.
Yeah, how much water does it take to produce, let's say, a megawatt of energy?
How much water does it take to produce? That would take a calculator. We could do it.
Yeah.
So a single kilogram is going to give you, it takes 2.3 gallons of water. And then going through a fuel cell, depending on what fuel cell you're dealing with, most of the fuel cells are going to take, this is why the efficiencies aren't so good, but fuel cell technology is coming along huge, is going to take somewhere around a kilogram, 1.8 kilograms to make the kilowatt on the reverse end. So the point that you have to make is if you can make the initial kilogram for close to free, then going back through the unit, even with the losses, you're coming out on top. That makes sense?
Yeah, but I was thinking more of not the cost of making electricity, but more of the impact or potential impact on the water.
Oh, that's why. Yeah, you get the water back from the fuel cell. It's not 100%. There's a lot of diminishing return there. But when we take the hydrogen and run it back through the fuel cell, so car is a fuel cell car. The fuel cells you saw in the picture, that's a Tesla. Those are fuel cells. The result of the recombination of hydrogen and oxygen is steady state DC electricity, about 48 volts, and water, a pure water molecule. What? Yeah, it's non-combustion. That's an electrochemical reaction.
Okay, so then essentially we're not losing any water.
No.
Okay.
But, especially if we're working with non-potable water, right? Because those are waste products. So, or rainwater catchment. That's another way of looking at it.
Yeah, I was curious how you designed the system to allocate solar inputs, photons, between battery storage and hydrogen production, and then how do you allocate the end use back into electrical use or powering the vehicles? And finally, which of those is more efficient?
Okay, so let me answer that in a couple of ways. So the hydrogen, anybody in here who does controls, And anybody who's working at all around a microgrids or an islanded situation knows that there are two things that these situations require. First of all, the transition from, for instance, grid connected to an island mode, you've got to be able to shed loads very rapidly, because you have to be able to buy time for the control system to figure out what's going on. How many of your resources are available to create power and put it back on the stream? Is it day or night? So on one end of the spectrum, you have what we call load shedding. On the other end of the spectrum, on a bright sunny day, we can have all of our batteries reaching full state of charge by 10 o'clock in the morning. So what's going to happen? Our voltage is going to begin to rise and our frequency is going to become unstable. And we're going to crash. Well, that's one of the beauties of the hydrogen electrolyzer. It is also a programmable load to us. And it's programmable in 3 steps of 10 kW each. So as our voltage begins to rise, we actually switch into hydrogen production, where if I were doing a pot farm or a ranch on the coast or something as an island, I would typically put a resistive heater somewhere with a fan behind it. And if this condition occurred, I would shove electricity to that resistive heater and vacate that energy into the atmosphere with a fan. In this case, I'm cracking water, making hydrogen, and storing it later. And we like to say that hydrogen stores instantly. It stores infinitely, is usable instantly. You can use it later. So then back, what do we use it for? Once we make the hydrogen, if we run it through our fuel cells, we're going to expand our fuel cells in the future. But if you look at what the fuel cells are capable of, they're capable of operating our system at night on base load. They're designed to follow our base load at night. And then we use it that way, but the real way we're using it is in our cars. So we're actually taking excess production and making hydrogen to run our cars. And our cars are 99.9% recyclable. We're starting to eat up into your lunchtime, so let's do it. Last question.
So, great presentation, Craig and Ryan. That was just fascinating stuff. You've mentioned that there's a workforce demand of 10,000 people like you, and a workforce demand of 250,000 people like your team. What discipline should we be focusing on? You've been mentioning controls, building automation systems all morning, or for as long as you've been doing your presentation. We're all over that. I think we have the pick and shovel thing down. We're good there. What's in between? What do we need to be training our students to do?
Well, the fellow behind me, I looked around the room and I saw those black boxes sitting there, and of course, being a nerdy wonk, I had to pick it up and I go, what is this? Right? Cool. We need all of those skills that you're doing, and that's why I was trying to leave you with a couple points. And I think starting to focus on more open source controllers is very important. I think that's going to be one of the keys to taking things like microgrids and nanogrids and spreading them out more rapidly. Get away from these high-priced control systems. Secondly, every one of you should, in some form, be introducing hydrogen to your students. And I'm vendor agnostic, but I would point out that Millennium Rain makes a teaching aid that's fairly inexpensive. It's designed around high school and college. It comes with a curriculum, an experiment manual, the answers and everything, to get people's heads involved in hydrogen, and then it even comes with a fuel cell. So you can go through the whole process with it. And then I would see, and I actually had an intern want to do this, is taking a device and actually, it's a manually controlled unit, but of course, instantly the human mind goes, well, why can't I automate this? Well, there's a huge learning experience right there, right? Because you got to make sure you have makeup water. You got to control the levels of the water and the hydrogen. You have to keep the current and voltage stable. You have to deal with heat. So I think those are the two biggest takeaways from our talk. Introducing microgrids is simple. I'm going to tell you, I think the name will change. Distributed energy generation is a better way of looking at it. I think that what we need to do is get you to expand your human production by a factor of 10 minimum. You know, here at Laney, they teach the building trades. Every person that they're graduating right now has a job in California. And I've been all over this country lately, and I see nothing but a building boom everywhere I go. So that's the problem when you have natural disasters, is all of the skilled people are already doing something. And then, of course, we can talk about it, but we're not allowed to reach outside the United States and grab skilled personnel and bring them in to help us with our problems. Which, that's a political thing, but it's a functional thing, because how in the hell are we going to build these houses? That's supposed to be the last question.
I just got one quick one to help everybody out here is, you know, a lot of us have a problem with understanding like what a line card would look like for your organization. What vendors do you use? Who do you use? Can we get a whole list of that from you guys so that we can start exploring the different vendors and the people that have that kind of stuff?
I'm going to leave a pile of my cards up here. Pam and Larry and Carlos. Any of them will get you connected to me. If not, we'll be happy to share that. You all have a personal invitation to come and take a tour of the facility. Come and learn. How can we help you? Our Phase 2 website, we're going to begin posting our operational system, and all of the data will be available so that you can actually have students go in and crunch numbers. You know, what's the efficiency of this? What's the efficiency of that? How do we do this? And hopefully in conjunction with a couple of manufacturers that I can't mention at the moment, there will actually be a microgrid modeling tool available open source. So a lot of things that we're working on.
Wonderful. Thank you, Craig.